And up next, we have Elena from the University of Virginia, who evaluated Google's protected audience protocol. So take it away.
Oh, good. Cool. So, thank you for the introduction. This is a joint work with my advisor, David Evans, and we're evaluating Google's protected audience protocol. So as we all know, since the introduction of the browser cookies, there have been ongoing discussions about their utilities and the threat to user privacy. As we can see, several papers brought up the issue within the PAS community. And since 2020, Google has been on the track of disabling tracking cookies in Chrome, and they proposed an initiative called the Google's Privacy Sandbox. This initiative aims to find alternative ways to help online marketing without the use of cookies. And our study focused on one of the proposals in the Privacy Sandbox, called the Protected Audience Protocol. It is designed for ad retargeting, and it enables advertisers to retarget ads based on some degree of user interest, but without revealing information about the user to them. The protocol can be summarized into 5 steps. We call a site that sells product the buyer side, and a publisher site that sells ad space the seller side. When a user visits a buyer site, it can attach an interest group object to the user browser, which stores information like the ads, the bidding script, etc. And later, when the user visits a seller site, it can initiate an auction, so that the browser will automatically run the bidding script in each eligible interest groups that this user has. And this whole auction process happens in the browser with some predetermined scripts provided by the buyer and the seller. And this is the key idea behind this protocol as they move the auction process into the browser from outside servers to protect user privacy. And after some time, the browser sends an event-level encrypted report to both the winning buyer server and the seller server. Lastly, the buyer and seller can query another trusted aggregation server with some encrypted reports, and the output will be one noisy aggregated output. There are 2 main ways to preserve user privacy as they propose in this protocol. And the first one is a k-anonymity check. This involves a server that ensures a minimum number of interest groups share the same value of certain check-in objects. There are 2 checks in the protocol. The first one happens during the auction phase and does not include the interest group name. Only ads that pass this check will be sent to the seller's code. So that is what we call the eligible interest groups. The second check happens during the reporting time. It further checks whether the interest group name is sharing among at least K users after the auction ends. So if this check fails, the browser simply won't send the interest group name along with the auction result to the seller's code after, so that it cannot be included in the report to track users. This is an intuitive design to prevent users from being identified through unique interest groups. However, I will introduce a way to circumvent it later. Another critical privacy mechanism is the design of auction reports. After an auction ends, the browser runs buyers and sellers code to generate event-level reports in the form of key value pairs and encrypt them before sending out to outside servers. This is very similar to the attribution API what Adam just introduced. And there is also a contribution budget limit, limiting the report value for each user, which is also the same L1 equals to 2 to the 16. And to decrypt these reports, the buyer can send them with a list of bucket keys to the aggregation server for only one time. This server aggregates value for each query bucket from the encrypted reports. Then it will add noise to each of them, each of the bucket key in a way that preserves epsilon differential privacy. However, this epsilon DP guarantee assumes the adversary can only has one buyer report for an auction, which can be undermined if they have multiple buyer accounts, which I will talk about later. Now we have a basic understanding about how this protocol works. The question we ask is, does the protected audience protocol actually prevent tracking? In our threat model, the adversary controls 2 types of sites. A primary site where users do not conceal identities, and the second site where users expect to be anonymous. The adversary also controls some other buyer accounts that can participate in the protected audience auction. We assume some users visit the primary site, such as a shopping site where they leave information like names, address, etc. and this corresponding to a buyer site in the protocol. Then sometime later, they visit the secondary site, which might contain sensitive information. The adversary's goal is to link these two requests so that they know who visited the sensitive site. To achieve the goal, the adversary can implement the following steps. When the user visits the primary site, the adversary can attach n interest groups, one from each buyer account it has, with a unique user ID in the interest group name. Later, when the user visits the secondary site, the adversary can let the n colluding buyers win n separate auctions. Then these buyers implement the same script for reporting so that the bucket value pairs in the encrypted reports are the same across n reports. And lastly, the adversary collects all encrypted reports about this visit, query the aggregation server, and can infer who made the visit based on the aggregated output. Since the user has a unique interest group name, the second K anonymity check actually will fail, and it will prevent the buyer's code from accessing the user ID. For now, let's just assume the adversary can access the UID here, and I will introduce ways to achieve this later. And since the adversary controls n encrypted reports for one user visit, this is the step that actually breaks the epsilon DP guarantee. And I will introduce 3 scenarios under this setup. The first scenario is very simple. The adversary has one predetermined target user, and the adversary only needs one buyer account so that when this target user visits the secondary site, this buyer will win an auction. Once the adversary receives a report, without the need to even decrypt it, they can already link these 2 requests and make a perfect, accurate acquisition. In scenario 2, we consider a more scalable linking attack. Let's say the adversary is interested in K-specific users. When one of them visits the secondary site, the adversary wants to identify the one user out of K candidates based on the aggregated output. In this case, all buyers use the user ID as the bucket key and the full contribution budget as the value in the reporting step. And the adversary can collect n encrypted reports with the same value. Then the adversary can query the aggregation server with K bucket keys on these n reports. And after getting the aggregated output, they simply accuse the user associated with the highest value as the one who made the visit to the secondary site. This figure here shows the relationship between the number of colluding buyers and the expected accuracy of this attack when epsilon is set to 1. As we can see here, with only 13 buyer accounts, the expected accuracy of this simple attack exceeds 99% when they target 1,000 users. And in scenario 3, we analyze the potential for mass surveillance. This is the same setup in scenario 2, but the adversary wants to identify some users instead of only one, based on the aggregated output. In this attack, for each visiting user, the adversary hashed the UID into a Bloom filter, using each resulting bit index as the bucket key. And for the reporting value, they just divide the contribution budget evenly across all reported buckets. And after querying the aggregation server with all received encrypted reports and all the bucket keys, for each UID in the large candidate pool, the adversary can compute a likelihood score and accuse some users with the highest scores. To evaluate the effectiveness of this attack, we ran simulations where the adversary controlled 20 buyer accounts, assuming there are a million user visits the primary site and 10,000 of them actually visit the secondary site. This figure here shows the relationship between the number of acquisitions the adversary make and the false positive rate of these acquisitions. As we can see, when the adversary only makes around 100 acquisitions, the false positive rate of the attack is extremely low, regardless the value of epsilon. The default epsilon in protected audience aggregation server is actually set to 10, and with 20 buyer accounts, the adversary can accurately identify more than 9,900 visitors accurately if they choose to accuse 10,000 users. And if the adversary has a low tolerance of false accusations, they can simply just choose to accuse less users. Now I'll talk about how to circumvent the K-anonymity checks using covered channels so that the buyer's code can obtain the user ID during reporting time. For a user, while the adversary creates a unique interest group name, these other fields are shared across at least K users. So the first anonymity check will just be passed once K users visit the primary site. The trick is that the adversary can embed the same set of creative URLs, which is the ad URLs, with UIDs into these users. So when an auction starts, the browser sends the whole interest group objects to the buyer's code, and the buyer's code can select the bid on the creative URL that matches the URL in the interest group name. After passing the first K anonymity check, the browser sends buyer's bid and ads to the seller's code. The colluding seller can give the ad that contains the UID information the highest score to let it win the auction. Then during the reporting step, while the second K anonymity check fails, so it does not include the interest group name, the winning creative URL will be included. Therefore, the seller can parse the UID from this ad URL and return it as the seller's message to the browser, which will be passed to the buyer's code later. In this way, the buyer can access the UID during the reporting generation time. There are also other covered channels to circumvent the K anonymity check. Please read our paper for more details if you're interested. So to sum up, our attack is based on using multiple buyer accounts to break the epsilon DP assumption of the reporting process and use covered channels to craft a unique interest group to each user and circumvent the K anonymity check. We highlight the result that with the current design of the protected audience protocol, even with all proposed privacy mechanisms correctly implemented, an adversary can still conduct mass surveillance confidently with only 20 accounts, which are not hard to obtain due to the nature of online advertisement. That's all for my talk. Now I can take questions.
Thanks, Helene, for the great talk and the interesting attack scenarios you uncovered. Do we have any questions?
Hi, great talk. Thank you, Elena. My question is, how do we detect this potential abuse? Should we look into interest group IDs or interactive URLs, creative URLs, I'm sorry? Like, how would you monitor this?
I think the best, it is very hard because all the code are implemented by the buyer and seller themselves, and the browser cannot really inspect them because they have different advertising strategy. I think maybe a way to detect this is to show how many buyers actually participate, like how many ad space. Because in order for 20 buyers to colluding and win auctions, you need at least 20 ad space that serves on the seller side. So maybe it can put some limitations on how many ads a publisher site can set up using this protocol.
Thank you. My takeaway from your talk, and also I think in the first talk, is that basically both the conversion API and this protected audience, whatever, both are susceptible to collusion. So it seems to be like a more fundamental issue. So
Yes.
do you think like there is a technical solution to this, or there will be like policy enforcement, like Google will make sure like an advertiser does not create 100 accounts?
Right. Yeah, I think it's a difficult question. Like I said, due to the nature of business of online advertisement, it is hard to prevent people from creating legitimate buyer accounts. But there can be some mitigations. Like I said, they might limit the number of ad space that can serve on a publisher side, or maybe they can use some other algorithms to provide the differential privacy that are not susceptible to these colluding schemes.
Thank you so much. Let's thank Elena again for the great talk.